Okay, so we've got diffusion and effusion. Two concepts we talked about before, but let's do a refresher. What are they? What is diffusion? Tell me. So what we have here is a bunch of gas in our first cylinder that's all in one area. That is an area of high concentration. Okay? So high concentration. In that example, every place else has low concentration. Would you agree? Yeah. When we talk about a gas diffusing, we talk about a gas moving from an area of high concentration into an area of low concentration until it is evenly distributed. Now, very often this involves two or more gases mixing and diffusing through one another, but not always. At the fundamental core of it, we're just talking about a gas moving from an area of high concentration to an area of low concentration until it's evenly distributed. Let me ask you this. At the point when it is evenly distributed and there are no more areas of high and low concentration, are these particles still moving?
Yes.
Yes. Unless we're at absolute zero, if they're still moving. Okay, good. Okay. Effusion is the movement of a gas through a tiny opening. So we've got all these gases over here. They are going to move through that tiny opening. One of the classic examples of that is a hole in a tire or a hole in a balloon. Now, when these gases, and eventually, you know, they'll balance out the concentration, all other things being equal and possible. Once we have equal pressures on each side. So the important thing about effusion, this is two-way movement. Particles are moving from this side out into this side and from this side out into that side. Now if you think about the pinhole or the nail hole in a tire, is there a lot of air going back into the tire? Why? Because there's a big pressure differential. And at the point when the pressure inside the tire is equal to the pressure outside the tire and it's completely flat and you're not going anywhere, there's air moving in and out of that hole. Okay? Things are moving in both directions. But that only happens once the pressures are equal. Okay, so this is the slide where we talk about rates of effusion and diffusion. This is straight from your notes. And we're going to do this derivation by hand because what I have found over the years is, I know, that if you just get handed the equation, it doesn't make a lot of sense, and deriving it by hand is far superior. So let's go to the next slide, and we'll start with a clean slate. Let's start off with this idea of Ke. What is Ke? Kinetic energy. What kind of objects have Ke? Objects in motion. So, does that describe anything you know in chemistry? Particles, molecules. So if we're talking about a gas, and we're talking about a gas with particles, which is any gas, those particles are in motion unless we're at absolute zero. What is Ke equal to? Do you remember? 1/2 mv squared. Mass times velocity squared, 1/2 of that. Okay, now, Ke is equal to 1/2 mv squared, but there's something we measure that's a proxy for kinetic energy. There's something that stands in for kinetic energy. When there's something we measure it every single day, we talk about it, and it's a proxy for kinetic energy. What is it? That was fast. What'd you say? Temperature, more specifically. But yeah, the temperature of a substance is really just a way of measuring its kinetic energy without measuring its kinetic energy. So if we have two gases, if we've got, I'll draw a balloon here. There's balloon A. And balloon B. If these two balloons are at the same temperature, so if temp A is equal to temp B, then guess what else is equal? Kinetic energy. KEA equals KEB. Fantastic. Okay, so if the kinetic energies are equal, what else is equal?
Temperature.
Okay, so if the temperatures are equal, the kinetic energies are equal. If the kinetic energies are equal, then 1/2 the mass of A times the velocity of A squared is equal to 1/2 the mass of B times the velocity of B squared. This is what we're going to start working with. So we're going to do some algebraic magic with our old 1/2 MA VA squared equals 1/2 MB VB squared. You know, in algebra, if we do the same thing to both sides of the equation, pretty much anything's legal, right?
Yeah.
What happens if we multiply both sides by 2? We get rid of that pesky 1/2. So now we have MA, mass of A times velocity of A squared is equal to the mass of B times the velocity of B squared. So we're going to rearrange to get our variables on the same side.
Wait, can we...
The step that I forgot. So when we talk about kinetic energy and we talk about mass, we're typically talking about larger objects. We're talking about cars and rocks and boxes and things like that. In the case of molecules, what's the thing that we most commonly would use as a unique identifier for mass, for the object, for the molecule? Molecular mass? Molar mass? Yeah. So we're going to change that to a large A, a large M. So now we have molar mass of A times the velocity of the particle of A squared equals the molar mass of B times the velocity of the particle of B squared. Okay, let's rearrange to get all these variables on the same side. Very important to note, whenever you are dealing with these ratios, and we're going to use the same basic equation that we're about to derive for both effusion and diffusion rates, these are always flipped. So if you've got your mass of A on the top here, your velocity of A will be on the bottom. It doesn't matter which one's on top and bottom, but they're always opposite across the equal sign. If we've got the masses on one side, whichever mass is on top will be on the bottom in velocity. So we'll take the square root of both sides. Let me ask you this, can we often or ever measure the exact velocity of a molecule? It can be done, but we're sure not doing it in a high school chemistry lab. The convenient piece for this is there's something that is directly proportional to the velocity of the particles that we've been talking about. What could it be? Effusion and diffusion. Because they are directly proportional, we can get rid of those velocities and we can put in the rate of effusion of B over the rate of effusion of A. So now we've got all numbers that we can actually obtain under these kind of conditions. The molar mass of A, the molar mass of B, and their relative rates of effusion. This is going to form a ratio that we're going to use a couple different ways. Okay, so this is the first piece of Graham's law that we've derived. The square root of the mass, the molar mass of A over the square root of the molar mass of B is equal to the rate of effusion or diffusion of B over the rate of effusion or diffusion of A. All right, so from our last slide, we've got our first derivation of Graham's law. Graham's law just says that the rates of effusion or diffusion of a gas are inversely proportional to the square root of their molar masses. Well, here's the other thing that we can do. There's something else that's related to molar mass, and that's density. So you've already used density and molar mass in the ideal gas law. So now what we can do is take this equation and say, well, the square root of the density of A over the square root of the density of B equals the rate of B over the rate of A. And we can use either one of these now to solve problems that involve rates of effusion and diffusion. Okay, so now we're going to go to page 355 in your book, Holt Modern Chemistry, and we're going to look at the practice problems number 1 through 3. Okay, so if we look at number 1 together, we're told this. A sample of hydrogen effuses through a container about 9 times faster than an unknown gas, which we're calling gas X. Estimate the molar mass of the unknown gas. So we've got our basic Graham's law equation. Okay, so we've got 4 variables that we deal with in this equation. The molar mass of hydrogen gas is known to us. What is that? 2.02 grams per mole. the molar mass of this unknown gas, gas X, is what we'd like to know. And what we know about the rates is that there is a relationship. I want you to be very careful here. Let's read that again. The hydrogen effuses 9 times faster than the unknown gas.
9 times H2.
So if you say 9 times H2, you're saying the unknown gas is effusing at 9 times the rate of the hydrogen. So the rate of the hydrogen is 9 times the rate of GX. Okay? And this, we don't know. I guess we're just calling it 1, but we're not going to plug in any numbers, so we'll even get rid of that. But this is a known relationship here, that the rate of the hydrogen is 9 times the rate of the unknown gas. Okay, the thing we are solving for is that. So let's go ahead and do our algebraic magic and solve. We divide both sides by the rate of gx squared, which gets rid of that over here. So now we have the molar mass of gx is equal to the molar mass of hydrogen times the rate of hydrogen squared over the rate of gx. Great! What now? Plug it in. I see a substitution coming. So we have this, which we can put in here. This is from our previous slide. Let's rewrite it. Okay, so now we're down to, this is something we know. The rate of gx squared disappears. And now what are we left with? The molar mass of this unknown gas is equal to the molar mass of H2 times 9 squared. Okay, so we get 163.62 grams per mole. With 3 sig figs, we get a final answer of 163 grams per mole for the mass of our unknown gas. Okay, so our final answer is 164 grams per mole would be the mass of our unknown gas. These problems aren't hard once you're used to them. This is the first type of problem you're going to have where you're comparing two rates and you're given the ratio of those rates. You know, the ratio of one is 9 times, 16 times, 4 times the rate of the other. Find a molar mass. Okay, so we're told, compare the rates of effusion of carbon dioxide with that of hydrogen chloride at the same temperature and pressure. In these kind of problems, when we have got both of the substances that are known, and we're going to have molar masses for both of them, what we're going to get as an answer is a ratio. When you set these up, it does not matter which one is on top and which one is on bottom. We can do square root of the mass of CO2, square root of the mass of HCl, and then which one's going to be on top for rate? HCl, because it was on bottom for mass. Rate CO2. Okay, these kind of problems typically I find confuse students, so I'm going to warn you in advance. You're going to get a single number. So go ahead and do these are not something where you're solving for anything, you're literally just plugging in and getting a number, but you are going to get a single number. So go ahead, do the math, and get me that single number. Take the square root of 44.01 divided by the square root of 36.46. Okay, how does this work? So I have 1.09867, etc., 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 equals the rate of hydrochloric acid, HCl, hydrogen chloride, over the rate of CO2. But that's two things, and this is only one thing. What does this work? How is this possible? There are two secrets to this. One is to remember that under every whole number is an invisible 1. Okay. So what we're saying here is that if the rate of CO2 is 1, the rate of HCl is 1.0986 times that. What that means in actual fact, what this means is that if this is 1 meter and this is 1.09 etc. meters, in the amount of time that it takes a particle of CO2 to effuse 1 meter, or to move 1 meter, the HCl is going to effuse, is going to travel, is going to diffuse, is going to move 1.09 meters. Okay? Your book did this problem in reverse. Okay, that finishes the notes for this chapter. Hold on. That's it, folks, for chapter 11. So, you've got time to work on homework. Homework due Friday, test Monday.